So in the first part, we measure out a known amount of the ammonium oxalate monohydrate, and then we determine how much KMnO4 solution we need to add to that. Now the important things here are that from this mass of the ammonium oxalate, we can get the moles of the ammonium oxalate, which gives us the moles of oxalate. We can use the chemical equation to find out how many moles of permanganate we need. And once we know moles of permanganate and the volume in which that many moles are found, we can get the concentration of it. So let's do that first of all for the first trial. 0.1883 grams, the ammonium oxalate monohydrate. Divide that by 142 grams per mole, because that's the molar mass of this with the water in there. And that tells us we have 0.00133 moles of the ammonium oxalate, which is the same as the moles of oxalate. So now getting the moles of permanganate, we see from the equation that 5 oxalates react with 2 permanganates, so thus we need less permanganate, fewer permanganates than the oxalates, so we multiply this number of moles by 2 over 5, which gives us 0.00530 moles. And then finally concentration is of course moles over volume. Moles we just got 0.00530, volume 28.8 cubic centimeters, which is 0.0288 cubic decimeters, or 0.0184 moles per cubic decimeter. Now of course, as a good scientist, you never do something once. So here we are, we did it 7 times. Each time different mass of the ammonium oxalate, which means a different moles of oxalate, so different volume of the permanganate solution, because we had to have different moles of the permanganate. And finishing the calculation off just like we did here, we get 184, 185, 183, 184, 182, 185 and 180. Now it's always worth, when you look at data, to see if there is an odd one out. And I would certainly say that the odd one out here could be the 0.0180. Now the question is that sufficiently the odd one out that we should ignore it? So here's what I do. If we use all the data, the mean is 0.0183 and the standard deviation, not bad, 0.0002, which is the last digit in this, so you'd expect a deviation about 0.0002. However, of course, if this is a fake piece of data, it's going to have an effect on the mean and the standard deviation. So let's see what happens if we leave that piece of data out. Well, the mean goes up by a smidge, standard deviation goes down quite considerably to 0.0001 instead of 0.0002, or see, it's more than 50% change there. Now the test that I use is that if a piece of data is outside, is further away from the mean by more than 3 standard deviations, when you don't count it in there, then it's too far out of whack. Now standard deviation, don't know whether you know the formula for that or not, but I'm not going to go through that here, but you can punch it in your calculators, you can punch it in Excel quite easily and so on. So anyway, this piece of datum here, 0.0180, is 0.0004 away from the mean value, and 0.0004 is 3.6 times 0.00011. So in other words, this deviates from the mean by more than 3 times the standard deviation, so therefore I would leave that out. So now let's go to the post-lab questions for part 1. Step 4, part 1, we had to heat the solution gently to about 80 degrees after adding some of the permanganate. Why is this, and what would happen if we didn't heat it? Well, obviously, any time you heat a reaction, it's going to speed it up. Okay. Now, why do you want this one sped up? Well, the reason is that on its own, this is not the fastest of reactions. And so if you were to just add a little bit of titrant and then add a bit more and add a bit more, you would never know whether or not the reaction had finished for your little bit of titrant that you add until you add more. It becomes a very difficult titration. However, the more that you do this reaction, the more it speeds up, because Mn2 plus is a catalyst for it. It's an example of autocatalysis, right? A reaction that catalyzes itself. In this case, because you got one of the products, acts as a catalyst for it. So therefore you add a bit in, you heat it up to speed that through, and then that makes you a whole bunch of the Mn2 plus, which means that as you continue on with the titration, the reaction will go nice and quickly because you've got the Mn2 plus in there. If you didn't heat it, The reaction would happen slowly. You wouldn't have much of this Mn2 plus in there, and a lot of times the reaction doesn't actually go from the colorless to the pink. You get this nasty brownish color, which is a manganese containing intermediate. Of course, you do have to heat it gently, because if you heat it too much, the oxalate will decompose to CO2. So it's one of those bits where you're damned if you do, and you're damned if you do if you're not careful with it. Part 2, already talked about that. Calculate the concentration of the potassium permanganate solution. Did I use all the data? What we calculated was 0.0184 molar. We didn't use trial number 7 because what we found is that if we left trial 7 outside, that when we took the mean, that's what X with a little bar over it always means, if we took the mean away from trial 7 or trial 7 away from the mean, then the difference was more than 3 times the standard deviation. And that 3 sigma, 3 times the standard deviation, is a really good test to see whether or not a piece of data should be included or not.